Welcome back to Summarize Science. Today, we're looking at one of the biggest hurdles for self-driving cars, the gap between how they perform in training versus the real world. End-to-end autonomous driving models are trained on massive datasets of recorded driving, and they learn to imitate human actions very well. In these open-loop tests, they can predict a car's future path with incredible accuracy. However, in the real world or a closed-loop environment, the car's own decisions affect what it sees next. This is where problems start, as even tiny prediction errors can accumulate and cascade into major mistakes, a phenomenon known as compounding errors. To solve this, researchers developed a new framework called Model-Based Policy Adaptation, or MPA. The goal isn't to retrain the entire driving AI, but to smartly adapt its decisions during deployment. The process starts with creating what's called counterfactual data. Using a highly realistic simulator based on 3D Gaussian splatting, they take existing driving scenarios and generate thousands of slight variations. They essentially create a what-if machine, asking questions like, what if the car swerved slightly here, or what if its timing was a little different? This exposes the AI to a much wider range of situations than what's available in the original training data. Based on this new, diverse dataset, they train two key modules. The first is a policy adapter, which you can think of as a co-pilot. It looks at what the main driving AI wants to do and suggests several small corrections or refinements. The second module is a Q-value model, which acts like an experienced judge. This judge evaluates all the different trajectory suggestions from the co-pilot. It grades them based on long-term outcomes, considering factors like collision avoidance, staying on the route, speed, and comfort. Then, it simply picks the trajectory with the highest score, ensuring the car makes the safest and most effective move. This image shows a perfect example of it in action. In a critical cut-in scenario, the original model struggles, while the MPA-adapted policy successfully brakes and yields to the other car. The results from their experiments are quite dramatic. When tested in both familiar and completely unseen environments, the MPA system significantly outperformed the original AI models and other baselines. Most importantly, in safety-critical scenarios designed to challenge the AI, the MPA-equipped agent was far more robust, achieving a much higher overall driving score. So, to recap the most important points from this research. The core problem is that AI drivers trained on fixed datasets are brittle and can't handle unexpected deviations in the real world. This new approach creates thousands of what-if scenarios in a simulator to generate richer data. It then uses a co-pilot model to propose multiple actions and a judge model to select the best one based on long-term safety. This makes the driving AI much more adaptable and robust, especially when things get dangerous. This kind of real-time adaptation is a huge step forward, potentially making self-driving vehicles safer and bringing them closer to widespread, reliable use on our chaotic roads. Thanks for watching Summarize Science. We'll see you in the next video.